Urs Peter. In my daily job, I try to be as much as possible with my hands in the dirt, writing Kotlin code. I'm also a passionate trainer, helping Kotlin developers to reach the next stage, no matter whether you're a beginner, intermediate, or advanced developer. Such I'm a certified Kotlin trainer. I speak frequently on conferences, so I'm a frequent conference speaker. Among other, I'm also a co-organizer of Kotlin Dev Day, which is a Kotlin conference that takes place in Amsterdam this year too, so maybe we see each other there. Well, enough about me. I would like to know a little bit more about you, and especially about your consumption of AI. So who of you is using a AI assistant for coding, like Copilot, AI assistant? That's by now almost everyone. Okay, this is kind of the standard today. So who is using some vibe coding tool, like the one we see just today, like Tuni or Cursor? Okay, that's less. I think if I ask over half a year again, then this might slightly change again. Who of you has interacted with an LLM in a programmatic fashion? Okay, also quite a few, nice. Who has brought an application to production that interacts with an LLM? That's considerably less. Okay. Let's see how this goes over half year from now. Well, if you talk about AI today, you're actually talking about these beasts here, right? LLMs, large language models. Today I'd like to look at LLMs from a developer perspective, assuming that for most of us it's just a black box. In order to interact with this black box, we need a running instance. We can get such a running instance on our local machine. These are the simple commands to run various open source models using the Ollama toolset. Quite easy to try. These are the commands, and off you go talking to an open source LLM. Of course, you can also run an LLM on your dedicated infrastructure, which allows you to send sensitive data to it, because it won't be abused. And of course, you can use one of the public offerings, for which you have to be careful that you do not provide sensitive data, because it might end up in the training set. However, if you take a step back, then an LLM basically is just another piece of middleware with an API we interact with as developers. It's a bit a special API, nevertheless, it's just another API. And when we have kind of structured communication with a piece of middleware, then frameworks aren't far. When we look at what we can expect in Kotlin land, then we have Coke. Nobody heard of Coke? Well, I would have loved to talk a lot more about Coke, but because it was released 70 hours ago, I didn't have time to dive further into it. So sorry about that. If this conference was next week, then probably we would know more about Coke. Well, the more established solutions we have on the GVM are basically LangChain for chain. Red Hat is behind that stack, which is based on the LangChain stack, initially created by Python, which is already around for quite some time, and it supports all these different things. If you now do not all understand what these all means, then there is good news. At the end of this presentation, you should know all these concepts and also should be able to leverage them for your own good. Well, then we have Spring AI, also 1.0.0, very recently, same for LangChain for J, 1.0.0, very recently, it's all cutting edge stuff. And when you look at the features, they're really more or less the same like LangChain for J. They have kind of feature parity. Of course, they have their strengths and weaknesses, but overall, I could say that they cover more or less the same ground. What's important to mention is that LangChain for Chain actually supports all server-side frameworks, and of course also you can run it on a rich client. So Quarkus, Myconad, Keter, and also Spring Boot, it also supports, whereas Spring AI, of course, is only for Spring. However, considering the fact that Spring has 90% of the market, it's definitely also a very interesting option. Okay, so if you'd like to interact with an LLM, this is how this more or less goes. First, let's take a look at LangChain for J. What I created here is a Keter application, and in order to communicate with my LLM, I need one of these, chat language model instance, which I configure here with some parameters. The crucial parameters for these models are more or less always the same. You need an API key, pay, right? You need a model name and so-called temperature. Temperature tells the LM how factual the reply needs to be. So 0 temperature, like cold, would be very factual, and high temperature, 1, would be kind of wild and fantastic. if you use temperature 0, this doesn't kind of prevent you from hallucinations. That's important to mention, right? 0 doesn't mean no hallucinations. Hallucinations is kind of a given when we interact with LLMs. Okay, once we have configured such a chat language model, then we simply can call its API, which we do as follows. You take some message, then you say generate, and then you get a text reply back. That's all it takes to talk to a language model, at least with these frameworks. I'm going to demonstrate this with a cool tool set. I'm going to use today Kotlin notebooks. There are also nice sessions that really dive into Kotlin notebooks. Today we'll see a variety of features of notebooks. So what notebooks allow us to do is, let me see, the following. It allows us to create some code snippets, which I then can call in other code sections, and it also allows me to define some markdown to kind of document what's going on. So here I define a code snippet to do a GET request to the newly created API I just implemented, and then we're going to ask which is the best Kotlin conference in the world. So let's see, finger crossed. It's Kotlin Conf, so no hallucination there. That's definitely for real. Cool. If you look carefully, then you saw this reply appearing all at once. But when you have a lengthy response, it would be kind of nice if you get it delivered piece by piece. And for this, we would have to use the streaming counterpart of such a chat language model, which we will do right now here. Internally, it works with a sync. You can convert it with a bit of glue code to flow. There are also some extension libraries already now for Kotlin that do this for you. It's not that hard. Well, and as such, it is compatible with how Keytor works with streaming data. And then, if we try out this particular setup, we see that now our response should be delivered piece by piece. There we go. And it's still Kotlin Conf, so kind of consistency here at LLM. Let's see how this works in Spring AI. The counterpart in Spring AI of this chat language model would be a chat client. If you put a bit of configuration in your Spring application, guess what? The same properties, API key, model, and temperature, and then I can simply interact with it as I did before. What Spring Boot does particularly well, LangChain for J, by the way, too, is the following. So sometimes I do not want to reply just strings, right? I would like to reply in a more structured format, like what you see here. So here I have a prompt that says select the most wanted dishes for a certain kitchen. And then instead of returning a string, I want it to be a dish. And this would be the data structure of my dish. That's what you see here, dishes with dish name and some ingredients. How does this work? Quite simple. So when Spring AI communicates to the LLM, it will analyze those data classes, generate a JSON schema for it, send this alongside with its request to the LLM, and instructs LLM to reply in this particular format. And LLMs tend to do this quite well. So I haven't had any hallucination on that level. And then we see, if we do that, that we do not expect strings, but a nicely structured JSON format. There it is. Okay. What Spring AI does particularly well, and LangChain a bit less, is so-called media queries, which look as follows. So I just have a prompt, detect all objects in image, and then I can provide some media, which requires the model to be multimodal, right? Not all LLMs support that, so the open source counterparts wouldn't do that, but OpenAPI does it. So I can provide an URL, literally an image, a voice fragment, whatever, and then the LLM would process that. That's what I do here. Again, a cool feature in Kotlin notebooks, I can depict HTML, so I can show some images, movies, whatever. And when I call now my endpoint with this particular image URL, then it would tell me what's on image. So by now I know that this bread here in the left corner is focaccia. Learned something today. Okay, so far so good. I mean, these are kind of nice demos, right? Kind of cool, but can you write something serious with that? I doubt. But we, of course, want to write something more complex, something that really is, to a certain degree, intelligent. And Apparently, this isn't that simple. By now, you have quite a few failures out there writing LLM-based applications, like the ones, for instance, here from McDonald's, that really had to take their chatbot, or it's not actually a chatbot, it was a voice-assisted ordering system, they had to take it offline because, well, people got 100 donuts delivered, for instance, even so they didn't order it. However, they started this project in 2019, where the state of AI, of course, wasn't as advanced as it is now. So let's see, maybe with the tools we have today, we can do a better job. Let's figure that out. But of course, you're not going to do something for fast food, right? We're going to create something delicious, the AI-powered Italian restaurant, Italian Delayed. So this is going to be your secundi after the lunch. Our application needs to actually do more or less two things, right? It needs to offer us a way to interact with a menu in ideally a sophisticated way. And also important, it needs to be able to execute orders. These are two capabilities we want. Which brings us to our first problem. How can I integrate my own data with an LLM? Right? In the end, this LLM needs to understand my menu, but probably out of the box, it doesn't do that because it's not trained with my menu. There are two ways to accomplish that. First of all, we could apply something called LLM fine-tuning, which is more or less taking an LLM, retraining it with my menu, and then I would have an LLM with my menu. However, this first of all is very costly, and second, if my menu changes, and it does on a weekly basis because I always have a weekly special, my LLM would be outdated and I have to retrain my LLM again. So that's probably not going to work very well for me. So this approach is often chosen for specialized models, like for instance the one we use for co-completion. The approach most businesses will use that want to integrate their data in a communication with the LLM is this one, Retrieval-Augmented Generation, short RAG. Quite a mouthful. However, conceptually, it's actually quite straightforward. It's not that hard. How does it work? Well, you have a prompt. You send the prompt to an application, and then the application would look up similar data to that prompt. Similar data to that prompt. Okay. And then this would be called the retrieval step. With the retrieved data, I would also add my initial prompt to it and send this to the LLM. And guess what? This is the augmented step, because you augment the prompt with additional data. And then, last but not least, we have the generation step, the LLM doing its thingy, taking the prompt and additional context. There is a more down-to-earth description for that, which is called stuffing the prompt. Makes sense to me. Okay, well, this sounds simple, but there is actually something interesting going on here. How can I find similar data to a prompt? How does this work? That's probably a different order of complexity than a traditional SQL-like query, right? In order to understand what's going on, we need to look at this interesting field here, NLP, Natural Language Processing, which is the field in AI that allows computers to understand and also generate human language. With that, I can achieve something like this, semantic search, also known under similarity search, which allows me to look for the word pasta, but also get back words similar to pasta, which is the ones you see here, spaghetti and so on. And interestingly enough, this also applies to whole sentences. So, what's going on here? Again, it's not that hard. The way this works is that words have meaning assigned by means of n-dimensional vectors. What is a vector? Well, it's just an array of numbers. And every dimension of this vector represents a characteristic of a word. Like here, index position 0 would be royalty, index position 1 would be masculinity, and so on. And then each word would simply have all these weights assigned, and as such, meaning can nicely be depicted. That's more or less the deal. Of course, the more dimensions you have, the more accurate you can describe a word, and the more performant your model will be, but the less accurate it will be. So, how are we going to assign those weights to these dimensions for each word? Probably not by hand, I guess, right? For this, of course, we would rely on training. So we would take a large corpus of text and then train our embedding model And over time, these relationships should emerge automatically based on our training set, right? So in this training set, most probably the word queen, reality, and femininity would be kind of closely related, whereas masculinity would be not very closely related to the word queen. And that's very important to realize. It really largely depends what kind of corpus I take. If I have a very specialized model, for instance in medical healthcare, then I definitely need a different data set to kind of depict the right relationships between the words. So which model you take is important. Once we have trained such a model, then we wouldn't talk about vectors anymore, we would talk about an embedding. That's the official term that is used, embedding, which live in an embedding model. Under the hood, it's actually slightly a bit different. It's important to be aware of that. We are actually not vectorizing words, but we're vectorizing tokens. And I'm sure you have heard the word token, because this is what you pay, right? When you interact with the LLM, you pay by token. So when you train such an embedding model, you also actually automatically create a so-called tokenizer. And that works as follows. So it would take a sentence like, the queen rules the kingdom, and would split it up in these tokens here. And you see that, for instance, king and dumb are 2 tokens. Why are we doing this? Well, the goal is to reduce our vocabulary, and as such, better capture semantics. And because our vocabulary is reduced, we are also now more efficient in processing it. Then we would simply assign every token to an ID, like de becomes 12 and so on, and then we simply have to look up such a token and get the corresponding embedding. The cool thing is, this also works for whole sentences. How is this possible? For this, we actually only need math, no deep learning and so on. So if we have, again, this string, the queen rules the kingdom, then we would take all these individual vectors of each token, and then use some aggregation algorithm to combine all these individual vectors into a single one. And what you see here is that, for instance, masculinity and femininity score more or less as high, because in the sentence we have king and queen represented. And as such, we also can represent meaning of a whole sentence, just by vectorizing it. Okay, you can get a way more tangible experience than just me explaining this concept using the toolset of, for instance, LangChain for J. Spring AI has them too. So what I have here is I have an open source embedding model, which you just can instantiate, and then it's there, the variety of them. Let's run this thing. And now I create an embedding for the word pasta. Let's do that. And you see this embedding has 384 dimensions. That's not that much, so it's probably not a very rich model. Believe me, beneath this embedding, it's a vector, right? It's just an array of numbers. And what do you think? How long is this vector? You guessed correctly. It's 384. It's the dimensions. It's the amount of elements in this vector. If you look how many tokens were used to generate that embedding, we see that it's 1 token. However, if I changed it with I love pasta, then we see that now we get 3 tokens. Okay. So why are we actually vectorizing words or tokens? Well, because then we are down to math, and this is what computers do very well. They can handle math. So what you can do now is actually create embeddings for different strings or sentences, and then compare the corresponding vectors using, again, some algorithm. And a very famous one is the cosine similarity algorithm. And as I said, the variety, this is the one you hear most in this context. And with that method here in place, I now could see how similar 2 words are. And 1 would be identical, 0 would be not similar at all, and we see that seafood and lobster is kind of similar to each other. However, if I say seafood and Kotlin, then probably it wouldn't be that similar. And just to kind of be really explicit about this, this also works for whole sentences. So the sentence seafood with spaghetti is very similar than lobster with pasta, but not with Cody prefers Kotlin. That has not a lot to do with each other. All right, so how can we leverage this concept for our application, right? We want to create something usable. Well, what we have to do is take now our menu and then figure out some text that we want to vectorize. And figuring out the text to vectorize, that's really an area of expertise by its own, because it's quite tricky to split up a large content base in a way that similarity search works. You have a lot of blog posts and a lot of different approaches for that. In our case, we keep it simple. So what we most probably do is we'll take something like the dish name and ingredients and vectorize that, hoping that when a user looks for ingredients or a dish name, he or she will find what he's looking for. Then now we have a vector. Then we need something else. We need a store for them, right? We cannot just keep them on our disk, so we have to store them in a so-called vector database. A bit more on that later. And then with the prompt, we do exactly the same thing. We take the prompt, we vectorize it, and from there on, it's vector against vectors, just pure math. So this is no AI. This is just math, number crunching. All right, and then ideally we can return similar items. Well, I said we need a vector database for that. The good news is that I assume most of at least server-side Kotlin developers know Postgres. And there is a very good vector extension for Progress, so you don't have to embrace a new exotic database to do some vector operations. There is, by the way, a talk soon about Redis doing that, so maybe also good to see that one. OK, so let's vectorize now our menu and store it in Postgres and see how we can achieve similarity search. For that, I first like to take a look at our menu. It's here stored in a CSV file, and you have this awesome, powerful building block called a data frame in Kotlin notebooks, which even, as you've probably seen also in the keynote, allows you to interact with your data in a typed way by generating code. It's awesome. So you see that here we have dish name, ingredients. And the stuff I would like to vectorize is what I do more or less here. I create some documents, and this is more or less what's relevant for this part. It's dish name with the separate ingredients. And this is what I would like to vectorize. So how can I now vectorize stuff? With these frameworks, it's a piece of cake. I declare an embedding store with all properties. For me, this will be the PG vector embedding store from Postgres. Then I define an ingester, which, guess what? Simply combines the embedding model I declared above and then uses this embedding store. And from there on, I can say ingest. OK, so now it's ingesting. That's what you see here. And with that, we should be now able to do similarity search. What's also cool about a data frame is that it doesn't only understand file-based data, it even can connect to a database and then can, well, talk to the data in your database. So that's what I execute here. And you see, this is what actually the ingester step has accomplished. It took the string I created and created an embedding for it. So far, so good. With that, we are at our destination. Now we're able to do similarity search. The way this works is, as already explained, I take some input text, a prompt. Here I just take some ingredients, vectorize it, of course using the same embedding model as the one I've used to ingest. That's important, right? If you would use a different one, then these vectors wouldn't match. You need to have the same model. And from there on, because I use Postgres, I simply can do a more or less traditional SQL query, just passing this vector as a parameter, with a new operator you probably haven't seen before, because this one is only available if you have this vector extension, which is this one here, representing a cosine similarity operator. So with this extension and this operator, it will do this cosine similarity comparison. And with that, I now get hopefully similar dishes, like the one I've entered here. And you see that it's kind of matches, right? Noodles, seafood, mozzarella cheese, tomato sauce, spaghetti with seafood, lobster, and so on. And if of course I raise the bar here, then I get a more accurate hit. So now we have create some vectorization. It's time to create our application and leverage this concept. For this, we're going to use Spring AI. But before we're going to dive into coding, I think it also helps to understand a little bit how this communication between LLM and our application takes place, what kind of structured format it has. Because it's not really that you send a string to LLM, it's a structured format. And it looks more or less as follows. So it's a message that contains different elements, and one of the key elements is so-called system prompt. You might have heard of it. This gives guidance to the whole conversation. Then we have the user prompt, which is what you as a user entered. alongside some additional context like the one we extracted from RAG. Then this will be sent to LLM. By the way, there's also something called tools, a bit more on that in a minute. And the LLM would then reply in the so-called assistant role. So as such, we actually know who said what. When you have a conversation, as humans, it's kind of logical, ideally, that you also kind of remember what someone else said before. Otherwise, you probably won't have a very pleasant conversation, that you would restart it all over again. So with LLMs, it's more or less the same, because LLMs are fully stateless. We need to preserve somewhere the state of our conversation. And the way this is done is quite simple. You simply would keep all the conversation you had before with that particular LLM, which would then be the chat history, which would be sent over and over again to this LLM for it to reason. And the LLM knows that the last message is the most important one, so it would not ideally take this piece of context as the primary input and then use the history only to support it. Okay. In Spring AI, to then communicate and also get data out of a vector store is, again, really a piece of cake. That's what you do here. So with a bit of configuration, I get such a vector store being injected. That's what you see here. I simply define some database URL, and also the algorithm I would like to use to compare those vectors, like here cosine distance. Then I take my prompt, look for similar documents, and then add these documents to the prompt I sent to the server, as you've seen also in the schematic representation. We, of course, need a system prompt. What are you going to do in a system prompt? Well, this is where prompt engineering comes in, and in my experience, there is really no engineering with prompt engineering, right? This is absolutely not the case. This is just trial and error, telling LLM, hey, can you help me with creating a system prompt? Trial and error, trial and error. This is how, well, the new way of programming looks like. Till I got so far, as you see here, it took me quite some iterations. So here we say you're an Italian waiter, you have to help someone ordering food. This is how you have to welcome someone, welcome to Italian delay. And by the way, you have also some additional context you can refer to well, do some smart things with it. And this would then be my augmented prompt I sent, the initial prompt from a user, and the additional stuff I added to this prompt. And with that, we now should be ideally able to get food suggestions based on some input. For this, I've created a, guess what, KMP application. This is my first vibe coding experience with Tuny. That's the result. Not only by Tuny. I also had a little share in it because Tuny wasn't able to do everything, but I have to say it did quite an impressive job. So, let's see how this goes. I say hi, and then we expect the greeting as defined in our system message. There it is, yeah, welcome to Italian DLI. This is the food I would like more or less to have, and it does, as I said, quite a decent job, because pasta, seafood, tomato sauce matches the dishes we see here. Okay, so far so good. But what we cannot do yet is do an order, right? In the end, I want to order a dish. For this, we need to look at LLM function calling, which again isn't rocket science. It works as follows. I have a prompt, and alongside the prompt, I do not only send some context I retrieve by means of RAG, but I also can send something called tools. A tool can really be anything you can execute. It could be an API, a web search, a database lookup, even a local file system lookup, whatever. Whatever you can execute is a tool. Then alongside each tool, I also send a description. And now I hope and pray that the LLM, when it gets the prompt, like I want to order, it kind of figures that, oh yeah, you want to order, then I have this tool called the function orders a dish. I think now it's time to call this order function. That's what it replies to the sender, saying, hey, now you have to invoke tool number 1. This application, at least Spring AI, would intercept that replies, not sending it to the user, and do as it is told, execute this particular tool. The reply of the tool will also be sent to the LLM, because there might be some valuable information to it or some error, and then the LLM can do, again, its reasoning thing before providing the final answer. This is LLM function calling in a nutshell. Let's implement that. In Spring AI, but also in LangChain for Chain, this is, again, really simple. The only thing I have to define is, and it's even full support for Kotlin, a function with an input and an output, data classes. I register it as a tool callback with a description, and that's it. And for now, I just do some logging here, because otherwise I get all this food ordered and think we're already full, right? So just do a log statement. And here, Spring would do more or less the same like with our structured queries. It would take those input and output, generate a JSON schema, and instruct LM, hey, if you want to call this tool, this is the format I want to have, so the LM would prepare that input as follows, and also know how to treat the output. Let's see if we are able to order our food. So, oh yeah, what you have to do, which is very important to mention, we also need to add this particular tool to our prompt. So the LLM is aware that this tool is available for its reasoning. I say I go for option 2, which would be this lobster, right? Spaghetti with lobster. And apparently it did well, right? It orders me in 20 minutes. Let's see, yeah, our tool was called. Where do these 20 minutes come from? Let's take a further look into what really went back and forth in this conversation, just the responses. You see here that the LM instructs in reply the Spring AI to execute this particular tool with this input. It did that. The tool then replies with deliver in 20 minutes, and this is what LM would be using for its reasoning. And what you see here above, by the way, is the chat history that went on. So it's quite lengthy payloads you would send back and forth. Okay, so far, so good. Well, what is created now is some sort of closed application that is kind of a monolithic thing, right? It's not possible to kind of leverage our functionality beyond our application. For instance, we could not expose a piece of our functionality to another LLM-based application like Claude Desktop. Wouldn't work. However, it would be nice, and it shouldn't be that hard, because if we were capable of kind of exposing those tools as something others can also access, so we would just take those tools and create some server of it, and then with a client and some protocol I could talk to that server, then other tool, like I said, Claude Desktop, that talks to another different LLM could, when it takes and uses the same protocol, talk to my server too. So by that, my functionality would become much more pluggable. And this is exactly where the model context protocol comes in. This is all again, pretty edgy stuff. It was invented in November by Anthropic, right? The Claude ecosystem. And because they kind of pushed it, it seems to become a standard. So OpenAI also announced to support it in their desktop application, and this is how things go in AI. Someone does something, and then if the rest thinks, okay, let's go more or less this direction, everybody runs behind it. We'll see if it's still alive in a year from now, but well, time will tell. Okay, so our server would then simply become an MCP server, which is really a very thin layer, a bit of glue code to actually expose either remote resources or local resources. So this is something that most of the time runs on a local machine in a fat client, not necessarily on a server-side application. So MCP server-side is a bit a mouthful for something small like a bit of glue that kind of forwards requests to one of these real resources. Then, of course, we need MCP client. Where does this MCP client live? They call this an MCP host. And we also need, of course, a protocol to talk to each other, which would be the MCP protocol, which is based on JSONRPC. Who has heard of JSONRPC? That's not many. Me neither, by the way. It was also new to me. Okay, and the cool thing is that this client can also talk to a variety of other servers. And as such, you can actually kind of incorporate a lot of different resources into the interaction with an LM on a kind of structured, protocol-based basis. Okay, so let's first take a look at an MCP server. What can it do? It actually exposes 3 different capabilities. The first would be that it allows you to return some prompt or prompt templates. Okay? It can deliver resources, which really can be data in any form, from a database, from file, whatever. And of course, it can also expose tools, just the ones we've seen before, for instance, do some ordering. The client's responsibility is to discover those capabilities. That's what it will do first, because a server doesn't have to expose all of them, at least one, of course. Would make sense. If the MCP server exposes a resource, then the client will also retrieve data, and the MCP client would also handle tool execution. The initiator of the tool execution will always be the LLM, but the MCP client would simply handle it. By the way, the MCP client is often a given. That's something you wouldn't write yourself. Java has a nice one, Kotlin has a nice one. Spring AI and LangChain, they use the Java implementation, but Kotlin has this MCP Kotlin SDK, where you also have a Kotlin-based MCP client, but also server framework. Okay, now let's take a look at the interaction. There are two transport protocols to talk to MCP server. The first one is, and that was a bit shocking to me, standard I/O. Well, this means that an MCP server really runs like a command line application, and then with system in and system out, you communicate with that server. So it's a highly stateful connection to that server. And that's why I probably not want to use those MCP servers on some backend with a lot of traffic. That's really something you have on a local machine that interacts with that server. There's also a remote counterpart, which is HTTP over server-sent events. If you don't know what server-sent events are, last year at KotlinConf, I gave a talk about them, so you might want to look at that talk. The transport protocol, as already said, is JSONRPC. And the cool thing about JSONRPC is that it's so simple, I can explain it in 2 sentences. 2, 3, 2.5. Okay, so this would be the payload to ask an MCP server, what are your capabilities? And JSONRPC, the selling point of JSONRPC is that it's not bound to a transport protocol, so not bound to HTTP with its post, put, delete, and so on. And because of that, it needs to define a way to say the receiving side what it needs to do, so what kind of action it needs to perform. And for this, we have this method parameter here. That's for one. Second, you have this ID concept, which is also a bit odd, but well, it works. So when I send an ID to an MCP server, this implies that I expect a reply with the same ID. That's actually what you say. If I don't send an ID, well, then it says that it would simply be a fire and forget call. This is JSONRPC in a nutshell. And the rest is just the payload you would define for whatever purpose you need it. Okay, so this is how the server would reply. It would mirror my ID, as already said, and then say what kind of capabilities it has. And this server is quite richly equipped. It has all the capabilities. Let's build our MCP server in a way that we now can expose our ordering functionality to not only our own application, but also to Claude AI. Okay, for this, as said, I'm going to use the Kotlin MCP SDK, which works as follows. I create a server with some name. I define the capabilities, which then, when I do the initial lookup, would kind of be returned. And then, of course, I need to provide some, for instance, resources. So what could be a good resource? Well, what we don't do yet is actually expose the whole menu. We have a very sophisticated way to find dishes based on some input, but maybe someone wants just to scroll the menu and see what kind of desserts there are. So for this, we actually could use such a resource. Having a name, a description, and then just whatever format I would like to return is, I use Markdown here. And you say simply server add resource. The next step would be to create an executable jar. Gradle jar, and then you would have executable jar. And then configure that jar in a configuration file that really looks like executing that jar. This is the format. You say Java, jar, and then executable we have created. And this file needs to be configured for Claude AI. So this is, you have here settings, and you have your developer. And here you see developer, so it's early preview stuff. Then this would be edit config, which would lead me to the config which we just have looked at. And you see here my agent is already configured. Okay, so let's see if we are now able to navigate the menu in a different tool using those MCP server resources. I need to select the resource explicitly. It's not just there out of magically. And what you see in the background is the communication between the client and the MCP server. And you saw that the client requested the menu, and I send it back. And now in my interaction with the LLM, it would take this resource into consideration. And it looks pretty good because it's from Italian delay. Okay, so far so good. We are not there yet. We still have to deliver a prompt and a tool, right? In order to do that, I need to refactor my original application a little bit to expose its capabilities in a more modular way. So what I don't like in this approach, by the way, is the following. No matter what prompt I send now to my application, I will always try to look up similar dishes. When I have some initial greeting or an order statement, well, it kind of doesn't make sense to look up dishes because you might confuse the LLM conversation. So I need ideally a better way to only look up dishes if it's about food. Let's see if we can do that. So what we would do is the following. We, of course, would expose here our order service. That's a given, that's the tool we had before, but now I'm introducing actually something new. I introduce a so-called classifier prompt. This prompt takes a prompt, that's the input of the prompt, and then asks the LLM, hey, can you classify what's in this particular prompt? And classify it as such that identify whether it's food or something else, and if it is food, also retrieve all the ingredients or dish names. That's basically it. And by the way, reply on it as a string, reply in this structured format. Classification type, food or other, and then food elements. So now I have extracted food elements of a prompt if they were there, and then I would also expose my vector search, but now not only with just a prompt, but really with the food elements. And as such, I hope to get much better accuracy, well at the cost of an additional interaction with an LLM. That's always the kind of trade-off we have. It will take longer. With that, I now can create my MCP server. So I simply would create now my tools here, which is quite a bit of code, but as I said, it's not that hard, right? I say server add tool, I give it a name and description, and here I just say, hey, if you get a reply, it's in this format, so that it can handle it better. Same for our find dishes service, add tool find dishes. Here I define a schema that says what kind of input it expects, so I can get the correct payload to call it. So this would simply be a key to HTTP call to the endpoint I just have exposed. And by the way, if someone has time, it would be kind of nice if we could create this JSON schema thing based on a data class. It would really help. Now I had to really call Tuny, and there were a lot of CO2 was just vanished because this is kind of hard to figure out yourself. A simple conversion tool would be nice. The same we do for our order dish service. Also here, we define a contract for our input. Then we call the API just exposed. And with that, we now should be able to order our dish. Also here, I have to do something else, by the way. I'm getting ahead of myself. What we also want, of course, is our prompt. So what would be a meaningful prompt? Well, the prompt we could use here is something similar like our system prompt we had before, in a slightly adjusted way, that it tells the LLM what kind of resources we have and which kind of tools we have. And as such, we hope that the conversation will be nicely guided. It's not strictly necessary, but it definitely can help, because it makes things more explicit. Okay, so now we have everything, resources, tools, and prompts. If I want to use that prompt, again, I have to do it explicitly. So that's what you just saw here. I have to select this particular prompt, the Italian meal agent. That's what you see in the background, again, happening. And from there on, it would guide the conversation with my LLM. So let's see if we can order food with this new approach. using MCP servers. Whenever it tries to call a tool, it has some security built in, so I have to grant that. So here it does classification, then it does the find dishes call. And if you look closely, it really extracted all the food elements of my prompt. So my classification approach has worked. Then I should now get a very accurate list of the food items that are applicable to me. Yeah, 5 minutes. So option 2, order my dish, and guess what? In again 20 minutes, my food would be delivered. Okay, so what are we still missing? Well, what we're still missing is a bit of a dessert, right? A bit the icing of the cake, the kind of next generation interaction between human and machine. Not only big tech can accomplish, but you and me. In other words, voice-based interaction with the system, where I talk to the system and the system talks back. And this is also surprisingly simple to accomplish to round this presentation up. So what I can do here is the following. I can use the so-called audio models of OpenAI. That's a feature only Spring AI supports for now, which does the following. I send some audio data to this endpoint. I convert it to text with this transcription model. Then I just would use the traditional chat I have used before, and then also convert this chat response to speech again. And with that, I should be able to talk to my machine as if it was 2025. Let's do that. I create an audio variation of my KMP client.
Do you have tiramisu?
We have both the classic tiramisu and eggless tiramisu available. Which one would you like to order?
I go for the classic.
Thank you for your order. You've chosen the classic tiramisu. It will be delivered in approximately 20 minutes. Enjoy your dessert.
Order completed. Yay! Well, so I hope with that we are able to embrace a future with AI and its manifold possibilities with confidence while enjoying a bit of dessert we just ordered with our newly created app. And as such, all leave this room as, hey, I rose. Thank you.